Hi there. In this video, we'll look at lesson 4.3, in which we explore the concepts of concavity and inflection points. And for this video, I chose an example from page 215, problem 8, and we're given this function right here. We're asked to determine the intervals on which the graph of the function is concave up and concave down. And in the problem set that follows, we're asked to find inflection points, so I'll just cover both of those concepts in using the same example. Okay, first thing, let's just get an intuitive feel for what it means to be concave up or concave down. And the key idea here is bending. So when we say the graph is bending up, technical word for that is concave up, but what does all of this mean? Well, let's look at an example to help with this. If you look at, and can I just go back for a second so that I can write on the screen? All right, and here we go. Oops. Okay. So imagine that someone was pressing down. Imagine like a wooden plank. The tangent line's a wooden plank. Someone's pressing down on it. When you move it to here, when the person presses down, now it'll be here. Imagine pressing down on that. Now it will be here. Imagine pressing down on that. Now it will be here, then here, then here. Okay. What we're seeing in this picture is that the graph is bending down. All right, it's bending down. At a certain point, however, it changes to where the person is no longer pressing down on the end. They're now pressing up on it. So now it's here. Press up. Now we're here. Press up. Now we're here. Press up. Now we're here. And what we see is that the function is bending upwards. Okay, so in summary, this part of the graph is bending down. This part of the graph is bending up. And the technical terms here are concave down when it's bending down and concave up when it's bending up. Okay, so with that, we have just sort of an intuitive understanding of what's going on. Also, if you were flying an airplane and you pushed forward on the controller, you would start to bend downward like that. If you pull back on the controller, your airplane would start to come up again. So that's another way to think about concavity. All right, so with that, let's go back to our flip chart. And let's make this a little bit more technical. So this was intuitive. Technically, the meaning of the phrase concave up is that the slope of the graph is increasing. Okay, so what does that mean? Let's go back to here and take a look. Whoops. Got to click on this first. And let's see what's up. So the tangent line is really steep right now. But as I move it along, it's less steep, less steep. Pretty soon it's a lot less steep to where it's not steep at all. And pretty soon it's going to be 0. Okay. And what's happening here, let me reset this, is that the slope of the graph is decreasing. The slope of the tangent line is decreasing. Still decreasing, knocking it down, knocking it down, knocking it down. Slopes decreasing, slopes decreasing, slopes decreasing, and stop. From here on out, the slope is going to start to increase. It's going to come up. It's going to come up. Right now, the slope is about 0. Here, it's not very steep at all, and now it's steeper, steeper, steeper. The slope of the graph is increasing. The slope of the tangent line is increasing. Okay, so that's the technical way to understand that. And let's continue from there. Okay. All right, for this next idea, so what we'd like to know here is how do I use calculus to determine where the slope is increasing so that I know where the graph is concave up? Well, yes, let's use what we know about increasing functions in general. In general, we know that a function is increasing if its derivative is positive. And that statement is true no matter what function we're talking about. So if we're talking about f, we know that f increases when its derivative is positive. If we're talking about f prime will increase when its derivative is positive. If we were talking about f double prime f double prime would increase where its derivative is positive, and so forth. The relevant one, though, here is that to know where f prime increases, we'll look to see where f double prime is positive, and that will tell us where f is concave up. This idea is called the concavity test, and it's summarized for you here. Again, f prime is increasing if f double prime is positive, and that concept is written out as the concavity test. Do you want to know where a graph is concave up? Look for where the second derivative is positive. Where is it concave down? Second derivative negative. So what this tells us is if we want to answer questions about the concavity of a function, we need to compute the second derivative and then make a sign chart to see where it's positive and negative. So without any further ado, let's go ahead and get started on that. And here goes. Okay, so I'm going to take this function and compute its derivative. Remember, this whole chapter is about applications of derivatives. And we're seeing one of the uses of derivatives here is that you can figure out information about concavity. Okay, have I done this math correctly? Let me check my work. Negative 4x cubed plus 12x squared minus 4. Whoops, I have not done this correctly. Minus 4, and then that part dropped out. Okay, so I've corrected my work. In order to determine where this quantity is positive and negative, I'd like to know where it's 0, and factoring helps me with that. You can factor out the number negative 12 and x. Okay, so if you distribute that, it should work, and it does. Okay, so now I'm going to make a sign chart, which will include information about y double prime. Here's the input axis, y double prime, y single prime, and y no primes. Okay, so this is 0 when x is 0, and it's also 0 when x is 2. So I should mark those special numbers on my graph, my number line, and we'll expect y double prime to be 0 here. If you plug in a number higher than 2, you're going to get negative and positive. So the product is negative. If you plug in a number between 0 and 2, you're going to get, let's use 1. You'll get negative, negative. So the answer is positive. And if you plug in a number less than 0, like negative 5 or something, you're going to get a positive factor and a negative factor, and their product is negative. So there's a sign chart for y double prime. Okay, so let's remember, y double prime is the derivative of y prime. If the derivative is negative, then the function decreases. If the derivative is positive, the function increases. If the derivative is negative, the function decreases. And next, this means slope. If the slope is decreasing, the function's concave down. If the slope is increasing,